Hey guys, so we're going to pick up here with chapter 6 notes. We already talked in class a little bit about this electromagnetic spectrum. The bottom line, okay, so the bottom line from our discussion is that the wavelength gets bigger as we go left to right in this figure. So gamma rays are the smallest wavelength, and radio waves are the biggest wavelength. And then the symbol we use for wavelength is kind of weird. It's a lambda, but you can write wavelength out if you want to. And then the other idea we had here on this slide was about energy. Energy is large, high energy on the left side. So in other words, gamma rays have the highest energy, and over here, that means low energy is on the other side. So radio waves are very low energy, but they have long wavelengths. Gamma rays on the other end of it are small wavelengths with very high energy. Okay. And again, we only see a very, very small part of the spectrum. Other animals can see more of the electromagnetic spectrum than we can. For example, a creature called the mantis shrimp, which is very freaky looking. You can look them up. Mantis shrimps, we think, can actually see almost the entire electromagnetic spectrum, including infrared and even microwave and all this stuff. So it's crazy. Their eyes are a lot more complex than ours, so they can see a wider range of wavelengths than we can. Okay. I'm going to show you this one in class. It's easier to look at this for real. These are theoretical, what we call line spectra. It's like a fingerprint for each element. So in other words, if we have the element neon, it's always going to have these wavelengths of light in it when we look at it with the apparatus that I'm going to show you in class. But the next topic is something really fundamental to understanding modern science. It's called the wave-particle duality. So duality means that something can exist in two different ways at once. In this case, we're talking about light existing as both a wave and a particle. So we call the particle of light a photon. Okay, so if we're thinking about it as just a point in space like this, that could be a photon. Then we're thinking about it from a particle perspective. On the other hand, when we looked at the wavelengths, we were thinking about it as a wave. All right, and so a wave doesn't exist in space. It's just one place. It exists throughout all of space like that. So that's what we're talking about here. Light actually is both a wave, so it exists everywhere at once, and a particle, so it exists in one place at a given moment. Now, there's no real great way of understanding that on a fundamental level. The human brain doesn't have a way of understanding it, to be perfectly honest. There's a lot of complex math involved here, but what it boils down to is, depending on the situation, sometimes we think about light as a particle, and sometimes we think about it as a wave. Sometimes we have to think about it as both simultaneously, and that's when things get kind of complicated. This is very different from the way that we experience normal matter and energy. Normally, you think of matter as existing in one particular place, and that's it. But we do encounter waves in nature, of course. If you toss a pebble into a lake, you make waves, right? And so that wave actually exists throughout quite a lot of the lake at one time. You couldn't point to a specific spot and say, well, that's that wave. Right? So that's kind of the same idea here with light. Okay. Now, ultimately, photons come from matter. They are either released or absorbed by matter, which of course is atoms. So that's where it's connected to chemistry. Okay. Sometimes the photons released from matter are going to be in the visible spectrum, and sometimes they're not. But here's how the process works. The basic idea came from Niels Bohr, and he said that the energy of electron, so the energy of electron is quantized, right? So quantized sounds a lot like quantity, and that's basically what it means. So it has a specific energy, right? A whole number almost you can think of, and we number them based on how close they are to the nucleus. So here in my atom picture, this is the nucleus. This is where my protons and neutrons are at. This is the first energy level. So we just say that, here we go, N equals 1 there. The second energy level is going to be a little farther from the nucleus, and the third energy level is the farthest one out in this picture. So it goes up as you go away from the nucleus. So this electron here is in the energy level N equals 1, and it can only exist in this very limited space, this very limited energy. Okay, it is possible that this electron might jump up in energy. That only happens if you shoot some energy at this atom and it absorbs it. Okay, so what's going to happen is we're in the ground state now, the lowest energy arrangement, because we're closest to the nucleus that that electron can be. And if a beam of light, oh my goodness, I went backwards. Here we go. If a beam of light comes in and hits this electron, it's going to disappear from where it was and reappear at a higher energy level. We call that higher energy level, meaning farther from the nucleus, the excited state. Okay, so again, we start off at the lower state, the ground state. We add light energy. And this is going to cause that same electron to disappear from ground state and appear in a higher level of energy. We can draw the same diagram. We can draw a diagram kind of showing the same idea anyway. Here, right? So if we start in the ground state, this is where we say N equals 1. So the nucleus would be off the screen down here on the bottom. And we add some energy, it's going to jump it up to excited state number 1. That would be the same thing as our energy level 2 on our diagram up here. And here's energy level 3, of course. All right, so if we added a little bit of energy, red light doesn't have as much energy as blue light. We can look back here at the spectrum. So red light is on the right-hand side of this visible spectrum right here. And so on the right-hand side, we said has lower energy. So if we're shining a red light on our atom, it means it's the lower amount of energy. So that means it's going to only go up 1 energy level, let's say. If I shined a blue light, that would be higher energy. It can travel farther. It's got more energy to expel to get up to the excited state. Now, excited state is not a stable place to be. So if we have an electron in, say, like the third energy level here, just as an example, that is going to fall back down eventually. And when it does, the energy gets released as a photon of light. So this little ball is supposed to be a little photon. If we're going from the excited state all the way back down, that photon can be released. So you get different colors of light depending on how big this energy gap is. So right now, the blue one is a really big gap. That's because it has high energy, because it's a blue particle. Red particles have a lower amount of energy. So that's how you could get that. Each element has a different gap between these energy levels, and that's how we get different colors. Okay. Elements with multiple electrons in them can have multiple transitions. We're going to look at the simplest atom right now. It's hydrogen, right? So we have 1 proton in the center and 1 electron that would orbit it somewhere. So there's my electron. Now, this electron is very stable when it's in the ground state, which is meaning close to the nucleus, right? So like this. However, a lot of the time, it absorbs light from the environment. Heat from the environment can do the same thing. And so this electron gets popped up into higher energy levels. As we said, excited states are not stable, so it's going to fall back down sooner or later. And it turns out that we can measure the energy of that transition. So if you go from the 4th energy level to the 1st energy level, as it turns out, that results in producing this purple line right up here. No, I'm sorry, this purple line correlates with the 4th to the 1st transition. If you go from the 5th excited energy state down into the 1st, you get this one. If you go from the 6th to the 1st, you get this one. This was an amazing discovery because we finally had an explanation for how matter and energy were related to each other. The transition of electrons from an excited state to a lower state was producing the colors of light that we see. And that's why each element has its own fingerprint, because the energy levels of its electrons are going to be different. So if we compare hydrogen and helium, their spectra look completely different. So their little picture here, their fingerprint, looks totally different. Hydrogen has 4 lines. We can calculate the exact energy of those and get a wavelength from that. And it matches this picture precisely. So this line spectrum data was the best evidence that Bohr's model of the atom was correct, that electrons do indeed have a specific energy level and they cannot exist in between. So when we're looking at the picture here, what that means is that you can't find an electron right here or over here, or even especially not at the center of the nucleus. You can only find them in certain places because electrons have quantized energy. Okay, so this is cool because this is the point where, from the video, the PBS video that you may have watched, this is when we started to realize that since each element has its own fingerprint using this device, we can find new elements. We can identify something that's different and new, and that set off a revolution in chemistry. So that was a really cool idea. At the same time, Bohr's work set off a revolution in theoretical physics, which is kind of what we use to figure out how matter is organized. All right. There's a problem though. Bohr's theory maps these colors perfectly. But if we go up to anything with more protons or more electrons, it doesn't work anymore. So there was something wrong with the math. We couldn't figure out why helium was unpredictable in its line spectrum, but hydrogen could be found. All right, so to explore the idea of quantized energy a little more, here's a nice diagram. Okay, people are not quantized. You can exist in space wherever you want to go. So here's an example. You could be anywhere on this ramp up to the chemistry laboratory. Electrons aren't like that. Things, in fact, anything on the small scale, like protons and neutrons as well. They're quantized. They can only exist in a certain place with a certain amount of energy, and that's it. So it's more like steps. Electrons can exist on the step, but not in between it. Okay, so those steps we symbolize as little, circles around the atom, indicating where the electrons can be. Okay, so it's very different. The quantized universe, the quantum universe, is very, very different from how we experience the regular world. It's really hard to imagine, but we do need to remember that it's true. So this idea of electrons existing in certain places is called the Bohr model of the atom. Now, because Bohr's model didn't explain helium or lithium or anything more complicated than hydrogen, further work needed to be done. So 2 players come into the story now, Louis de Broglie and Erwin Schrödinger. And now Schrödinger is an interesting character because he was a statistician. That means he studied statistics. And statistics had never been applied to chemistry at that point, or even physics. They use it a lot in biology, of course, but Schrödinger was the first person to have the idea of using the kind of rules of statistics to try and figure out what electrons would do. So here's the Bohr model, right? We've seen this as kind of a classical representation of how an atom looks, where these electrons are only in certain spaces and they kind of make like a sphere around the nucleus. It's more accurate to picture electrons as probably existing in a certain area. So you see how dense these dots are? That means you're really likely to find an electron somewhere in that space. And as we get further and further away from the nucleus, the likelihood of finding an electron in that area decreases. Okay, so in the quantum model, which is from Schrödinger, we picture electrons existing in a given area as probabilities. Okay. All right. Now, this leads to a more complex but more accurate description of what these atoms actually look like in terms of where their electrons are at. Everything is organized kind of based on Bohr's energy levels. We call that the principal quantum number, or also sometimes principal energy level. And the symbol for that is always an N. As it turns out, the principal energy level is really easy to find on your periodic table because it's just the period number for the main group elements. Okay, now just to remind you of what a main group element is, right? I'm gonna show you a periodic table here that I have on my computer. A main group element is anything in group 1, group 2, and groups 13 through 18. So these transition metals in the middle don't count for that. Okay, and neither do the ones at the bottom, the lanthanide and actinide series. So keep that in mind when we're looking at this. Now, if I have a principal energy level of 1, so if my N is 1, 1 can only have a sublevel that kind of matches. So there's, if the energy level is 1, that's the lowest energy level we can have. There's no energy level 0 for electrons. You can only have one sublevel. Okay, we call that level S because it's shaped like a sphere. Okay, the symbol for sublevel is an L. It has some fancier names in mathematical ones, angular momentum and so forth, but for our purposes, we're just going to call it the sublevel. And if I have one principal energy level, I can only have one sublevel. All right. If I have 2 as my principal energy level, that means 1 is still possible. It's still in there, but I have electrons in the second level as well. So that 1s, so this is the energy level, that's your N value, and this is that sublevel we were talking about, the L value. So you still have the 1s in there, but in addition to that, you have a second energy level. And in the second energy level, you start to have 2 different choices. So you have 2 different sublevels. You have one that we call the S still, so that's still shaped like a sphere. And we have another one that we call P. I have no idea why. If you find that answer, let me know. I've always wondered. But the P orbitals look kind of like 3 bow ties all stuck together. Each one of these orbitals represents the probability that you're going to find an electron in that location. It's about 90% likely. Now, what's interesting about that is that it means 10% of the time you could find that electron way far away from the nucleus, and that is perfectly acceptable. So sometimes I like to imagine that one of my electrons might be on the moon right now, or maybe on a beach in Jamaica. Okay, and that's entirely possible. There's always a possibility of that. Of course, the farther away I imagine my electrons going, the less likely that it is, but it could still happen. Okay, now, it's a lot to remember where the energy levels are and all these things, but the trick of the thing is that the periodic table tells you almost everything you need to know. So the period number is on the side, the left side of your periodic table here. I'm just going to jot this down on my copy here. Okay, and we have to remember that the actinides belong here. You can always follow along with the atomic number, and the lanthanides, the purple ones, belong in period 7. And of course, our version of the periodic table is completely filled in. This is an old picture, but it'll do for now. The main group elements are highlighted in colors here. Those are, of course, groups 1 and 2, and then 13 through 18, as we said. So for these main group elements, the principal energy level of a particular element comes from whatever period it occurs in. So like here, if we look at what is that? Let's see, I think that's potassium right there. If we look at potassium on our periodic table, we see that it's in period 4. So potassium has a principal quantum energy level, which we symbolize with N because that's a lot of words, of 4. Okay, so I want you to tell me for carbon, what is the principal energy level? I want you to tell me for, I don't know, let's see, magnesium, what is the principal quantum energy level? And let's do one more. Let's do sulfur. Okay, so answer those 3 and I'll grade them when you turn your notes in. So those sublevels we were talking about are also called orbitals. Okay, so orbitals are the shape of the probability where 90% of the time you'll find an electron. Groups 1 and 2, let me go back here. I'm just going to draw on here. Groups 1 and 2 are what we refer to as Well, I don't know what that symbol was. Let me see if I can erase that. We refer to groups 1 and 2 as the S block, S like Sam. So 1 and 2, this is the S block because the sublevel is shaped as a sphere. Groups 13 through 18 we call the P block because they're shaped like those little bow ties. Okay, so the groups give you an indication of the sublevel and the periods give you an indication of the energy level, the highest energy level. So the S block, again, that's in groups 1 and 2, is just a series of spheres. So you start off with the lowest energy one, which is the one closest to the nucleus. Okay, and then if you go down a period, you have energy level equals 2. So we're in the second period. You still have the 1s orbital there. You just stack on another layer. So this is a sphere. And in between these two things, so if we cut this in half and look at it, in between these two things, kind of where this white zone is, the electrons are not allowed to go. That kind of correlates with Bohr's model of the atom, right? You have, well, pretend like these are circles. You have the nucleus in the middle, and n equals 1 would be the first one, n equals 2 would be your second circle here, and n equals 3 would be the bottom one. And in between each layer is a space where electrons cannot go. Okay, so this doesn't disagree with Bohr's model, it just improved it. It improved it because we realized that not all electrons exist as a sphere. Okay, but the important thing is we have these nodes. Node means new electrons. They are not allowed to go there. So this supports the quantum idea of the electron where it disappears from one place and appears in another one, and it does not exist in between. That means electrons teleport, which is pretty cool. Okay, so the p orbitals look like this, sort of like little bow ties. One p orbital is this green one. So we can draw a version of that ourselves. And there's 3 p orbitals in total. So one of them goes up and down, the other one goes to the right and the left. They're supposed to be symmetric, but I'm freehanding this on a computer, so you'll probably do a better job on your notes. And then the other one actually goes front and back, so it would really look like it's coming out at us here. And it would also go in the back. That's hard to show, so frequently people draw that one, kind of a diagonal, okay? And so what we have here is the p orbitals. There's 3 of those, all right? There's one S shape, one sphere for each energy level, but each energy level on the p orbitals has 3 different places it could go. Now the electron can teleport from here to here. That doesn't change the energy. Those have equivalent amounts of energy. I could teleport from the blue one to the yellow one. Again, equivalent amount of energy. That's not changing energy level. It's just changing place. Okay, so that's an important concept. Now if we go up to the next period, the third period, we still have the 1s orbital. We still have the 2p orbital. Now we get something weird in the fourth period actually, but the third energy level. Okay, you get a d orbital. So the d orbital occurs in the fourth period where the transition metals are. So basically what happens is that the transition metals have so many electrons that that d orbital is actually lower in energy. It's closer to the nucleus. Lots of negative charges, and they condense down and want to be close to that nucleus. So the fourth period transition metals are what we call the first d orbital, which has an energy level of 3. So we abbreviate it as 3d. If we're in period 4, it has a 4s, a 4p, and a 3d orbital as its highest energy levels, its outermost electrons. The f orbitals, we call them, happen farther down in period 6. And the lowest energy f orbital in period 6 is called the 4f. So it's the 4th energy level, but it's shaped differently from the others, from the s, the p, the d. Okay, and as always, there are spaces in between each level where electrons are not allowed to go. All right, so here's what the d orbitals look like. I don't expect you to be able to draw these. I just wanted to show you how many there are. We have 1, 2, 3, 4, 5 different d orbital shapes. Okay, and each one of those stack up. So here this drawing has the 3d orbital here, the 4d. So we have the 4d there, and we have the 5d on the top here. And what you notice is in between each layer is a node. And also in between these different shapes are some nodes where the electrons are not allowed to go. All right, so that happens for all different orbitals, not just for the s and the p. Now, what's interesting is each one of these shapes can fit 2 electrons each. So we can fit 2 electrons here, and 2 here, and 2 here, and so on. So we have 5 shapes. So for the d orbitals, we have 5 shapes, 2 electrons each. So we can fit a lot of electrons in one d orbital. We can fit 10 in all the d orbitals together. The F has 7 shapes, so there's 7 different shapes. Each of those can also fit 2 electrons. So we can fit 14 electrons in the F block. All right, so then for the P block, it goes from 13 to 18, groups 13 to 18. The P block has 3 shapes. They all look like bow ties. Each one can contain 2 electrons, so that can fit 6. And for the S, of course, we have one shape. It's just a sphere with 2 electrons.